Hello, calculus students. I hope you are doing well. This is the video for section 3.2 in your Calculus 3 class, Math 213. And this section, 3.2, has to do with vector valued functions, of course, but especially with the derivatives and integrals on vector valued functions and what they mean, as well as some of the interesting properties about the derivatives of vector valued functions. So I hope you will learn this well. This is not going to be a very difficult class. Difficult section. All right. So I hope you'll learn this well. All right. Let's get started. All right. Section 3.2. Let's go ahead and write that down. All right, the topic is the derivatives and integrals of vector valued functions. Mostly we'll be focusing on the derivatives, all right? So here's the definition, and you will like this definition because it's easy. If I didn't tell you this definition, you will probably figure this out on your own, okay? So let's say we have a vector valued function. You know what that means. That means we have one parameter, often referred to as t, and that's going to give you the x, y, and sometimes the z coordinate. And so we have r, which is defined on the set of real values. Sometimes, maybe there are exceptions, like if you have a tangent or a log or a 1 over x or something. But anyway, it takes almost all the real values into either 2 or 3 dimensional space. Okay, so then the derivative. You can write the derivative in different ways. So here's a standard way, right? The one you prefer is probably the one with this prime. So r prime is equal to the limit as h approaches 0 of, does it sound familiar? R of t plus h. So this will be the vector, which is slightly beyond when t is equal to this number, right? So t plus a little bit minus r of t. So this will be a small vector. The difference between these two vectors, you divide this by h, okay? If it exists, because sometimes this limit may not exist. All right, so this is not surprising, right? You have seen this kind of thing before. Let me try to draw a picture of this. If this is your RT, remember it's just a space curve, right? So here is your point, R of T, and a little further is your point R of T plus H, and the difference is, of course, this little vector. And if you make it smaller and smaller, what happens is it doesn't basically shrink, okay? And in fact, the length of this vector may actually be longer than this. But the point is, as you get h to approach 0, this will get closer and closer to the tangent, okay? And because you're dividing by h, again, it doesn't necessarily become smaller, and you will see this in a moment. And so this is our derivative. You can clearly see it has something to do with the velocity of this, right? And so it is one of the first things I will mention. The first thing is this derivative is tangent to the curve at this point where, r of t, okay? And it is also, oh yeah, I didn't tell you this. It also turns out to be, and you can go ahead and try this. It's really simple to prove that the derivative is equal to the derivative of the x component, the derivative of the y component, the derivative of the z component. Okay. Now remember, I told you this is actually an easy section, and that's because there's really nothing new that you're learning in terms of differentiation here yet. Okay, so if you look at page 273, this is a pretty obvious fact. If I didn't tell you this, you would probably just do exactly this. You just take the derivative of each part. It's not as obvious as you may think, but the application or the proof is really not that hard. Okay, so here are our applications. Let's say if r of t represents the position function of something that's flying moving on the plane or flying in R3. Okay, so if you assume that this is the position function where t represents time, and this is really the most important application of vector valued functions, right? So when you take r prime, okay, what do you get? Well, that is the velocity function. Let's go ahead and use the colon here, velocity, okay, at time t. If you take the second derivative, oh, by the way, I should probably mention this can be written as d dt of r, okay, and that is that. And then this is d dt of d dtr, so we write it d dt, and so because it's d dr on the top, oh, it sounds like Dance Dance Revolution. Now it's d and then r. Denominator is dt times dt, so this is dt square. I know this notation, it looks really weird. It's almost like somebody made a typographical error, but it's not. So sometimes people write this, not very often. But the second derivative is the derivative of the velocity function, which we know, what you know as the change of velocity, which is acceleration. Now notice here, all of these are vector valued functions. Okay, so the result of these, if you evaluate them, they will give you vectors and not numbers. But there is one thing that is a number, and that is if you take the velocity vector and take the norm of it, which is, you can write this as the length of the velocity vector. What do you call the length of the velocity vector where the direction doesn't matter? Okay, this can be calculated by, well, you know, because r prime is basically this. Okay, so the way you calculate this is you take x prime, evaluate that at t, and you square that. That's your first component. The second component is similar, and the third component is also similar. So basically, you take the square root of the sum of the squares of the components. And this is otherwise known as what? What is the length of the velocity function? Yes, that is speed. So the speed is still a scalar or a real function. All right, let's do a simple example. Nothing hard, right? All right, so this is the time for you, if you feel uncomfortable, time for you to review all those differentiation formulas, including some of the properties, right? So for instance, if you have the difference, I mean, if you have the derivative of a sum, of course, that's the sum of the two derivatives, right? And then the difference, the derivative of the difference is the difference of the two derivatives and so on. It doesn't work so simply for the product or the quotient, because you have to use the product rule or the quotient rule. Here is your function, secant, tangent, and then 4/3 pi. What is the velocity derivative? I mean, what's the derivative, which is the velocity? Well, secant, okay. So remember, secant is 1 over cosine. And so you can apply that, or you can just remember secant has the derivative what? Secant tangent, okay. Do you remember the derivative of the tangent? That's secant square, okay, and then 4/3. That's it, right? If you are asked to find the velocity of this object, where this is your position vector, right? If this is your position vector, what is the velocity at t is equal to pi over 6? Okay, so this is like this is a typical question that, for instance, a rocket scientist or an aircraft engineer might be asking, like, hey, let's say, what's the velocity at a certain, time t, and if this is your, if r is your position function, then v of t, you just plug in pi over 6. So this will be secant pi over 6, tangent pi over 6, comma, secant square of pi over 6, and then 4/3. And then you just have to figure this out. Remember what the secant is? So here's pi over 6 is 30 degrees. All right, so the idea is this is one of those standard triangles, right? A 30, 60, 90 degree triangle. The ratio of the sides are 1, 2, and square root of 3. And so the secant, what's a cosine of this function? Cosine of 30 degrees is the square root of 3 over 2. So the secant will be 2 over the square root of 3. Tangent is this over that. That's 1 over square root of 3. All right, and then of course secant, I already established the secant is 2 over the square root of 3. Let's square that, and then the last one is 4/3. All right, and so this is 2/3, and looks like it's 4/3. 4/3. Simple enough. All right, what's the speed at pi over 6? I guess I'm not asking a question, so that should not be a question mark. I'm really picky on grammar, so. All right, so that's, find the speed of this object at pi over 6. So what is that? Okay, so for that one, you find S is equal to, it's basically the length of this thing here. So it's 2/3 square plus 4/3 square plus 4/3 square. And you can see that the denominator is, of course, 9. You have 4 plus 16 plus 4. Right? No, sorry. 4 plus 16 plus 16. And that is 36. Okay, so this will be 6 over, actually, that's square root of, that square root of 4, that's 2. Okay, so that's how you can find, oops, what happened to my 2 here? Yeah, okay. So that's how you can find the speed and the velocity and so on. Here's a theoretical definition. We say R of t is, what's the word? Differentiable. And what does the word differentiable mean? It means you can differentiate. At a particular point, t is equal to a, if r prime of a exists. Very simple, okay? It could be 0, but if the derivative exists, it's called differentiable. Okay, so remember to use, what is that? Well, first, I should say, if you have t squared, it becomes 2t. If you have t cubed, it becomes 3t squared. So use the power rule. My computer is not very cooperating here. Let me see if I can fix this problem. Okay, so use the power rule, also the product and quotient rule, and more importantly, the mother of all the rules, the chain rule, okay? And chain rule should be really a second nature to you, and you shouldn't even notice that you are using the chain rule here. Okay, so in terms of when you do differentiation, and you will have lots of questions where you have to differentiate a given vector value functions. I'll let you do that on your homework. Let's just talk about differentiation rules. You don't need to prove these things, but let's say you have R of t, which is, x, y, z. And let's say f of t is a real valued function. Sometimes you have a mixture of a real valued function and a vector valued function. And let's say c is a constant in my list below, okay? And now everything I'm going to say is pretty much what you expect. So if you have the derivative of a constant multiple of a function, what do you think this is? C times, a derivative of, well, no, C times the some vector value function. What is the derivative of a scalar product? Of course, it's a scalar product of the derivative. So that's something that you sort of assume it's true, right? And then what happens if you have the sum or the difference of two differentiable functions. That would be r1 prime plus r2 prime, or minus, depending on what the original sign is. So that's the sum and the difference rules. Okay, so what happens if you have a scalar function, a real valued function, multiplied by a vector valued function? Now the result is of course a vector valued function because it's a scalar times a vector. And so that is okay. What happens if you take the derivative? Any guesses? You may just guess that the same thing as the product rule works. And that is absolutely true. You can prove this if you really want to. I believe proof is in the book. So it's the derivative of the first times the second plus first times the derivative of the second. Now notice here, that's still a vector valued function. This is a vector valued function. So the answer is still going to be a vector valued function. This is sort of a product, it's a product rule, not the product rule. Okay. Now what happens then if you have the two vector valued functions dotted together? So this is now a scalar function, right? Maybe it's important to emphasize this. This is a real valued function. Okay, so if you have this dot product, what is the derivative of this real valued function? And again, you may have guessed it. It's the derivative of the first dotted with a second plus first dotted with the derivative of the second. Is that really true? Yeah, it turns out to be true. And again, this is a vector valued function because you have a dot product plus a dot product. Okay, so this is also a product rule. What happens if you have the cross product and take the derivative of that? Do you think it's r prime, r1 prime cross r2 plus r1 cross r2 prime? Do you think that's the case? It turns out to be so too. Right? So the product rule still works. There is a version of the product rule for a scalar product of a vector valued function, the dot product of two vector valued functions, and the cross product of two vector valued functions in 3 dimensions, of course. So these are all now called product rules because they all seem to be similar, right? And then what happens then if you have R composed with a real valued function? So this would be a situation, for instance, where you have a vector valued function defined not just in terms of t, but in terms of f of t. Maybe that's t squared or t squared plus log of t or something. Okay? So now R is a function of ft, a real valued function. If you take the derivative of this, okay, then well, how does it work? With a chain rule, you take the derivative of the outside, multiply that by the derivative of the inside function, right? If the chain rule is true, and it still is true. Okay, so this is the chain rule, another version of what we learned as a chain rule. Notice here, this is real valued. This part is vector valued. And so this is really a scalar. You should write this first, maybe, right? This is a scalar, this is a vector, and the result is a vector valued function. So this is sort of like the chain rule. Everything that you expect to hold true does hold true. I will be going over a couple of these things again in maybe a couple of sections later, but you should know these things. Okay, should I do a problem? Yeah, before I go into the integrals, why don't you do this? Go ahead and do this. All right, so I have this r of t. You have cosine of 2t, sine of 2t, and t. All right, so this is going to be a helix, but I want you to find vt and the speed when t is equal to pi over 2. Okay, go ahead and find this, and when you are done, you can come back and then we can work on this together. And then we'll go into integrals and other things in this section.